in this next video, we're going to be talking about another type of dimensioning, which is called datum dimensioning. So we've looked at chain dimensioning, where all of these are chained together, all 5 of them. The last one we looked at was broken chain dimensioning, where 4 of them were chained together. The top one is the overall length, and so the run out was right here at this gap. This next dimension, called datum dimensioning, is a little bit different than each of these, in that all of these now are going to go away and not be dependent on each other. Datum dimensioning establishes what's called a datum point or a locational edge. So what that would look like would be, so here's 1, and here's 2, and here's 3, and here's 4, and here's 5. And of course, you have your arrows on there like that. In this particular style of dimensioning, this edge becomes what's called the datum or the reference edge. This datum point here is what controls everything else. Okay, so in this case, keep using the same decimal numbers, 1.000, so that's still the plus or minus 5 thousandths. The next one here is 2.00, 3.00, 4.00, and then the top one here was 3 place decimals, 5.000. Okay? In this particular case, it's going to be a tighter tolerance than the 2 previous ones, even though the decimals are still the same. So for the first step, it was 3 place, 2 place, 2 place, 2 place, 3 place. Okay, so we've kept those in line, but now they're not accumulating tolerances. So one dimension to the next, to the next, to the next, we don't have those tolerances adding up or accumulating one on top of the other. The reason is because each of these edges are now standalone points from this datum. So a lot of times you'll see a datum edge or a datum point, sometimes it'll have a symbol. That symbol may be a circle with a cross in the middle. A lot of times there will be colored out spots like this. You can see that there. So this type of symbol would be a reference to a datum type symbol. With datum dimensioning, that is dictated simply by all these arrows being on the very edge here. Okay? In this particular case, the overall length, and by the way, I did go ahead and write up those numbers for our chain dimensioning. The length range was 4.96 to 5.04. The length for the broken chain was 4.995 to 5.05. In this particular case, the overall length, the maximum length, would be the 5.000 plus the unspecified tolerance of 0.005, which would be 5.005. The same for the minimum, 5 minus 0.005, which gives you the 4.995. So the overall length is now still the same as the broken chain, because that overall dimension is still the same as what it was before. The difference, though, is if we were to look at any one of these others, okay? The first one would be unchanged because it's the same as the previous 2 examples. But each one of these now do not have accumulated tolerances. So in both the chain and the broken chain, as we dimensioned, the tolerance from this one would be added to this one, and these 2 would be added to the next one. In this particular case, we no longer have that. So this part is actually going to have tighter tolerances, and this part is going to be all referencing this one edge, or at least for all these dimensions here. So we no longer have these tolerances here accumulating. Each edge stands on its own. So if we were to calculate, let's say the midpoint, it's still going to be the plus or minus 0.01 for that midpoint edge. Okay? Whereas with the chain and the broken chain, there's going to be more wiggle room. I do want to go ahead and highlight, though, let's say we wanted to look at this one, and if we wanted to calculate the maximum and the minimum of this middle point, okay? We would do the same as what we saw in the previous video for that run out. Here in the middle point, the 3 would go out as far as it can, so that would be the 3.00 plus the 0.01, which is the unspecified tolerance. So for the maximum, we would take this edge right here, and we would put it as far as we can that way, which would be the 3.01, which is our 3 plus our unspecified tolerance. This edge right here, we would take as far as we could this way, which would be the 2.00 minus the unspecified tolerance, which is 1.99. If we were to subtract 3 minus the 3.01 minus the 1.99, we would get the maximum width of this, which in our case would be 1.02. Okay, so that's the maximum it could be. Now we want to look at the minimum. The minimum, we would do the same thing, but in reverse. So this edge here would go in as far as it can go. This edge here would go out as far as it can go. So going in from this edge would be 2.99. This going farther this way would be the 2 plus the unspecified tolerance of 0.01, which would be 2.01. We subtract those out and we get 0.98. Okay? So in this particular case, it's still going to have the wiggle room, okay, between this tolerance and this tolerance, or the dimensions with those tolerances. But it's not going to be dependent on the 1, it's not going to be dependent on the 4 or the 5. For this middle one, it's just these two edges here. The range, if I had to calculate out the range, we would just simply subtract the 1.02 minus the 0.98, and that gives us 0.04 as our range for that middle section. Okay? So this is what we call datum dimensioning. I'm going to show you this in a different example here. So let's say that we have a part, and let me just go ahead and erase this here. So, used to know a guy who worked at a tool and die manufacturing plant. They did a lot of die stamps, and they did a lot of datum dimensioning. Okay, so let's take, for example, this plate right here. If we had to locate all of these holes and locate these out quickly without getting a really messy drawing. Now, you can see that this is a very busy part. If we dimension this with chain or broken chain dimensions, you're going to have arrows all over the place. If we did it the datum dimensioning style we just looked at, we would have a stack of dimensions from here all the way up to here with a whole bunch of numbers. Instead, for datum dimensioning, what they'll do is they'll specify a corner, and then they'll run all the rest of the holes as just simply a line call out. Okay? So here's what that would look like. If we had, let's say for example, a plate, and that plate had a bunch of holes here, and a couple of big holes here, and let's say a little bitty hole here. What they would do is they would come in and they would establish the datum point. So for here, maybe the datum point would be this corner. And they would just simply label it as 0.00. It'd probably be a 3 place. And so they'd just simply draw a line out, draw a line out, draw a line out. By the way, in AutoCAD there is a function where you can dimension with datum dimensioning. And when you do, you establish the datum, you just pop in these points, and it automatically builds this in with the numbers. So here, let's say that it's 0.75, 2.25, 3.5, and so on. Okay? What these numbers are they're a reference to this datum point right here. Same for this edge. This edge here being a datum point of 0.00. Okay, and so they would just simply would list out like this right here. And they would put lines, and they would simply put these down. So let's say quarter, half, 1.00. Okay, so just for the sake of time here, I'm just going to write some of these down real quickly. Okay, and so the rest of these obviously would be filled in. I'm not going to just make up a bunch of numbers. I'll just put some squiggles here to represent some numbers up in here, okay? So they would just simply line these dimensions up, and instead of running a whole stack of dimensions showing the same edge, they're just now putting locational dimensions of saying that this hole is 3 inches away from this datum edge, okay? So that is functionally how they would go about dimensioning a datum dimension part, especially one that has a lot of holes or a lot of features. that need a lot of different dimensions. Datum dimensioning is generally a more precise way of dimensioning. Once again, the more precise, the tighter the tolerance on the part, the more your costs go up. If you're dealing with, let's say, tool and die punching, if you're dealing with automotive design, if you're dealing with aerospace design, areas that you need extremely tight or extremely precise dimensioning, then you need to use extremely precise dimensioning. If you're at a place that can have a lot of loose tolerances, so something like, say, a welding or metal fab type shop, maybe an HVAC shop where the ductwork has a bit of play and you're fabbing out ductwork or what have you, in those cases you might be able to run with much looser tolerances. And of course, the looser the tolerances, generally the cheaper the cost, because it's a quicker, easier process. You don't have to have as much advanced machinery if you have to get super tight or super fine on tolerances. And by the way, I'm talking about like if you pluck a hair and slice it into 10 pieces, you know, that's about 2/10,000ths of an inch. Some machine shops can hold that tight of tolerance, which is super, super tight, but it costs a lot more money to do than somebody who's just running a handsaw, you know, cutting a bar stock, for example, where it might be plus or minus an eighth of an inch. So just something to keep in mind as we talk about these accumulated tolerances and how they interact.